Okay. Hit it.
We don't know where Mike is back in a second.
Here it is.
Sorry.
Okay, hit it.
You guys ready? All right, first off, I want to thank everybody for coming, and thank you for allowing us to be a part of the Capstone program. My name is Michael Sheck.
I'm Nathan Wilk.
I'm Connor Kamicki.
I'm Rakim Laharvik.
I'm Wanda.
And we're here to present EzBar. First and foremost, we're going to go over what EzBar is, followed by a breakdown of our team. Then we're going to go into how EzBar works, and then ultimately discuss our plan to mitigate risk, test, and produce our project. Imagine that you're at a bar. The bartenders are swamped, running around to take orders, and you're stranded at the bar waiting for what seems like an eternity to get served. What happens when orders are coming from every direction and the bartender loses track of who came there first? We at EzBar plan to mitigate the frustration, lack of organization, and ultimately improve efficiency of bars everywhere. EzBar is an automated bartender which plans to improve bars and pubs all across America. We feature a Raspberry Pi microcontroller which is used to drive our solenoid and control our flow of the liquid. We also feature an on-system user interface which allows you to easily pick a drink of your choice. We're also developing a mobile maintenance application which allows management of your EzBar system with ease. Lastly, we're also incorporating a security system which features RFID technology, and we're also building a website to promote professionalism and act as an outlet for people to keep track of our EzBar's progress. Here we're going to go over the team. My name is Michael Sheck. I'm the project manager here at EzBar, and I am also the lead GUI developer.
I'm Nathan. I'm the RFID and database designer.
I'm Connor. I'm the hardware and database designer.
I'm Rakim. I'm the head mobile application developer.
I'm Wanda. I'm the web and database developer. So a couple of requirements for our system. One, it has to consume low power, so it is cost efficient for the establishment. We also want it to have a desired flow rate, so it is able to compete with the pouring speed of a bartender. We will build a system for safety that will make sure or help prevent underage people from accessing the machine. It will have a capacity of 10 bottles to give more options to the customer, and also this machine will be easy to maintain. It will have an Android maintenance app. It will have a cleaning system. It will have an easy to change bottle system, and also it will be easy to use from the user interface.
So just an overview of all the different components of our system. As was said before, we have our mobile application, then we have our on-system application running on our embedded controller. We have our RFID system, we have our databases for all the storage of our information, then we have our hardware control system and flow control system working together, and lastly our cleaning system.
So this is our system model. Once a customer is allowed through the security system, they can access the user interface where they can choose their drink. This information is sent to the system application, where information is sent to the database and in certain circumstances the mobile application. Information about the drink is sent back from the database to the system application, where that information is sent to a hardware circuit to control the right valves in order to make the correct drink for the output.
So we're also making a mobile application to maintain the EzBar. This application is currently being developed on Android OS, but in the future it will be developed for iOS as well in the Swift language. We're also implementing a login system to differentiate between the different establishments and to make sure the data is secure as well as our databases. This app will let you view or edit the inventory as well as receive alerts and notifications depending on if what your stock is, depending on if a bottle is empty and how much of each item is left, as well as statistics on the usage and finances of the EzBar, such as how much you're making per bottle, how much is left of each bottle as I said earlier, and things of that nature. And this is the Android user interface.
EzBar will feature a user-friendly graphical user interface. On our right, you can see our current graphical user interface. This is actually embedded on our proof of concept. Currently, it's able to accurately pour 1 ounce of liquid But later on, we're planning on implementing various sorting options, such as sorting our drinks that we offer by liquor, mixer, and even the top 25 of the bar.
So our RFID system satisfies two things. One, which is safety, and two, which is a bar tab. So when you need to implement safety, because make sure that anyone at 21 is not able to access the bar. To do that, we'll have the bartender be able to give out only verified RFID tags, people who they've proven 21. So with these individual tabs, we're going to be able to keep, or individual RFID tags, we're going to be able to keep tabs of what everyone's bought and how much of it they've bought. With that information, we're going to cross-reference that with government statistics that show number of drinks versus intoxication. So that way, when someone's reaching a number of drinks at the level of intoxication, we'll have the app notify the bartender, and we'll leave it to the bartender's discretion to cut someone off.
So this is our hardware control circuit. Our solenoid valve is actually modeled by R1 and L1. Our solenoid valve actually needs 12 volts to operate properly, but we can only achieve 3 volts out of a driving microcontroller. So we built up this system. The capacitors C1 and R3 also work to lower down the ending power that's going to be dissipated across our transistor Q1 when it turns off. So this is the power that is across the transistor. Right when we switch it off, it spikes up to just under 120 milliamps, and then it's going to dive back down and flatten out around 10 milliamps. The transistor we're currently using is actually rated up to 625 milliwatts. So we're well underneath the recommended amount. So this is the current through the solenoid. We need an initial spike of 100 milliamps to fully pull that pin in against the spring, but then we can actually cut back the current to allow and just hold the pin in. And this also lowers the power dissipated, again, across the transistor.
So in order to maintain the quality of our drinks, we need to implement the cleaning system. This cleaning system can either have two options. One option is to have a water tank built into the system and have a pump to flush the system, or we can hook it up to a faucet in the bar and also flush the system. We're testing two different options for the timing of the cleanings, either a certain amount of drinks poured or the last time the system was cleaned.
So for our flow control, we use Bernoulli's energy equation for liquid flow. And the way we plan to implement it is that when we figure out a fluid flow that is competitive against a bartender, we're going to have to design our system for a certain height to achieve that flow. So that top equation is our modified Bernoulli's equation, where you're going to have the gravity times the height of your system, where the height of the system is defined as the bottom of the bottle down to where the spout is and pours into the glass that they're choosing. And so then it's going to be equal to our fluid flow speed, which is going to be defined as our flow rate times our cross-sectional area of the tube that we chose to use squared over 2, plus our summation of minor losses. The summation of minor losses is defined as, in the bottom left corner there, as this Moody chart number times the length of our tube times this fluid flow speed again squared over the diameter of our tube times 2. And so this Moody chart number is we use through a reference graph. And so since we're in laminar flow, we end up having our Moody chart number be 64 with a Reynolds number. And this Reynolds number in the bottom right here is defined as the density of our liquid times our fluid flow speed times the diameter of our pipe all over the viscosity of our liquid. So for our drink database, we broke it down into a similar template to what's shown on the right here. We're going to have a liquids table, which has the liquors and the mixers such as your rums, your whiskeys, and also your orange juice and your cranberry juice. Our recipes table is going to have the name of the recipe and the number of ingredients. And the ingredients table is going to be broken up into about 5 or 6 tables depending on which number of ingredient it is. So that way when we pull a recipe, it'll know the number of ingredients, so it'll know the number of tables to pull from.
So for our databases, we are using MySQL. The website database, some features or some things that it does is it gives content such as text for the web pages, and it also keeps track of what accounts are able to edit the web pages. For security measures, the website database does have such things as stored procedures and error reporting. We have tested the defense of our website database using an application called SQLmap, and it was successfully able to defend against any SQL injection. So the purpose of our website is to show people who we are, what we're doing, why we're creating this project. The website was developed with a content management system called WordPress. And to run this website, we needed to use a shared server, which we rented from GoDaddy. This server also allows us to have 10 databases. It gives us a file management system to easily organize the website, and it also gives us emails.
So here are some of the standards that we're going to be using. That first one is a major one, which is the New York law, the SLA 92.1. Using the minimum requirements to have an automated electronic liquor dispensing system. The second one is the IEEE 802.11n, which is specific for the onboard Wi-Fi of our Raspberry Pi. And the last one is the EECE410 256-2007, which is for RFID technology.
So we have obviously we're running into a couple things that we are worried about. So the first one is what happens when our system loses connection from Wi-Fi. Since most of our data is stored on a database, we won't be able to access that. So what we plan to do is to create a smaller, scaled-down version of all of our ingredients and recipes that we're going to store on a local database on our system. So that way when we do lose Wi-Fi connection, we can still operate with some functionality. We also plan to implement a check system that will send a notification to the maintenance app on when that system does lose connection from Wi-Fi. Next we thought about, well, what happens when we lose power? Since we're using normally closed solenoid valves, they're only open when they have a power applied across them. So in the event of a loss of power, they will all remain closed, preventing the leakage of product. And again, as we said before, we're using databases and we want to make sure all of our recipes and information stored on there is secure and nobody has access to that. So luckily WordPress has some built-in features, and we're going to be making some of our own stored procedures and ensuring that all the PHP scripts we use in accord with a mobile application use safe functions.
So as I mentioned earlier with the RFID, we want to limit the drinks that someone has if they're intoxicated, but at the same time we also don't want to cut someone off who, let's say you're at the bar, you buy cold drinks for your friends, you may only consume one, but the RFID will say you bought in 6. So we also want to prevent anyone from not being able to buy a drink. So that's why we're leaving it up to the bartender's discretion to cut someone off. Another problem that we encountered was theft. If someone steals our RFID tags, we don't want them to be able to come back at a later date and be able to access our machine. So to prevent this, we're going to try and implement a way to delete the tags from the system without needing the physical tag present.
Since we're mounting our bottles upside down, we need to account for the possibility of our bottles leaking. If the bottles do end up leaking, this could ultimately damage our circuitry as well as result in a loss of product. In order to prevent this, we're going to make sure that we purchase high-quality bottle toppers. Since we are doing a Kickstarter campaign, there is a possibility that we won't get funded and we won't achieve our goal. Should this problem arise in the future, we plan on self-funding this project out of our own pocket. And lastly, we're planning ahead in order to assure that we do not fall behind our schedule. We are incorporating various unforeseen events that could arise next semester and are including this into our scheduling.
So for our test plan, we are moving up from our proof of concept design, which has already been made, to our prototype design. This includes having 10 bottles on it, having the RFID system, and other features. As we add parts, we will be testing along the way to make sure that if there are any issues, we can get rid of them right then and there. Towards the end, when we do have our final product made, we will stress test it by emulating a bar scene where multiple people can make multiple different drink orders on the machine over a long period of time to make sure it's ready to be put in an establishment.
So for our bill of materials, we need to do a cost analysis of our project to determine what our budget should be. We need a Raspberry Pi 3 with a Raspberry Pi touchscreen, as well as a breadboard kit with various electrical components with it, as well as tubing, a solenoid valve, wood for encasement of our proof of concept, as well as an RFID reader and RFID tags to come to a grand total of $348.80.
Here you can see our schedule for the fall of 2016. In the blue, this is some of the milestones that we've achieved. Over the course of the month of September, we completed our research for our solenoid valves and our flow control. We began developing our website and began a cost assessment of all the parts that we're going to need for our project. Going into October, we began developing our maintenance mobile application on Android, and we also began developing our GUI. Going into November, we continued these projects that we started in October, as well as began developing our database of mixed drink recipes and whatnot. And then we also completed our proof of concept design. And going into December, we actually began our Kickstarter campaign. Going into spring 2017, we plan to scale up from our proof of concept to our prototype by the end of February. And then throughout the months of March and April, we plan to further improve this proof of prototype in order to further resemble a final product. And then finally, in May, we plan to present this final product. A Kickstarter is basically a crowdfunding platform which, with a mission to promote projects and fund projects that have some type of creativity behind them. We're using Kickstarter because we want to acquire some extra funding that we don't think that we'll be able to get from the school. as well as get our foot in the door in the startup community. The purpose of Kickstarter isn't to sell your product, it's to sell the idea behind the product. For our Kickstarter campaign, we're asking for $1,000. That includes everything that we discussed in our cost analysis, as well as all the rewards that we'll be offering for a donation. Some of our awards are going to be shot glasses, koozies, and even t-shirts.
So ultimately, we want to provide an easy and efficient way to pour a drink while reducing waiting times. We want to ensure that we follow standards-driven design and mitigate any risks as they come along in our project. We also want to follow a strict test plan. Any questions?